The last video in this unit will be on implicit differentiation. This is another technique that we use to find the derivative in functions that cannot be written explicitly in terms of y equals x, with all one variables on one side and one on the other. So sometimes it's easier to write it in implicit form, and so we're going to discuss the difference between the two and work several examples finding derivatives using implicit differentiation. So on this screen you can see that we have two different types of functions. We have an explicit form of a function where one variable is going to be written in terms of another. So y equals, so all the x's could be written on one side and then all the other variables written on the other side. You can see here though that this is a parabola function, right? Here's another this is the same function, but it's written in implicit form where the x and the y are on the same side. This particular function can be written either way, explicitly or implicitly. These two, b and c, are actually this one in the implicit solved for y, realizing that this is not a function. So when you solve it, you have a top half and a bottom half for the same function, solving for y. However, C, down here C, where the x's and the y's are all mixed up together, there is no way to write that explicitly. There would be no way to take the derivative if we didn't have a new technique for using that. So in an implicit function that cannot be written explicitly, we have to use implicit differentiation. It doesn't mean that we can't use it for other functions as well, but sometimes it is slightly easier to take the derivative of an explicit function. So once again, the reasons that we use implicit differentiation is because the function cannot be written explicitly or the resulting function is too difficult to deal with otherwise. All right, so we're going to need to have a little bit different notation when we work with implicit differentiation. So when we see something like dy dx, this is going to mean the derivative of y with respect to x. So that means that I've got two variables in my function y and x. And then if I had this, because I'm going to have two variables, right? I'm going to take the derivative of y with respect to x, and then I'm going to take the derivative of x with respect to x. So this is what we've been doing all along, right? And so it's been understood that when we take the derivative of x, that we are not continuing, because we're taking it in terms of x. This is actually a form of 1, right? Dx over dx, if we were, to think of it that way. But it's just understood. So anytime you take the derivative within an implicit differentiation problem, the derivative of x with respect to x, we do not have to use this notation, dx over dx. We can, but it will always cancel out and go away. All right, so we will frequently also in a implicit differentiation problem, the final answer will yield a derivative expressed in both x and y. And that's okay. That's okay. Oftentimes we're going to solve for something, but we may still have an x and a y in the equation. So dy dx, and then dx dx, and so we'll talk about that. Let's do an example. So here's some guidelines for taking the derivative of implicit equations. First, differentiate both sides with respect to x. 2, collect all terms involving dy dx to either the right or the left. This is to the left and move things to the right, but you could move them to either side. Factor a dy dx out of the left side of the equation and then solve for dy dx. So here's our first example. We're going to find dy dx if y squared is equal to x. All right? So to find dy dx, we're simply going to differentiate both sides of the equation y squared equals x with respect to x, treating y as a differentiable function of x and applying the chain rule. That's not too much. It's a lot simpler, though, if you'll just look. So here's my function, right? I'm going to take the derivative of this side, right? The derivative of y squared is 2y, and we're going to differentiate y with respect to x. That's the chain rule, right? So 2y dy dx equals the derivative of x, which is 1. Now, the chain rule looks like this. D dx, remember this notation? Y squared equals d dy of y squared times dy dx. And so we replace this with 2y. Right? So that's what we're doing here. Now, the next thing it says is to solve for dy dx, because we're trying to find dy dx, and that's going to be 1 over 2y. Okay, not bad. Not bad. All right, here's another example. So we are going to write y equals xy squared, and we're going to differentiate both sides with respect to x. So the derivative of y is 1 dy dx. And then on the other side, I have the product rule. The product rule. Okay, over here, product. So that means the second times the derivative of the first plus the first times the derivative of the second. Well, the second is y squared, so that's going to be 2y dy dx. All right, so the goal then is to get the dy dx to the other side so that I can factor it out. So let me rewrite it because I have a lot of extra stuff here. Dy dx equals y squared plus 2xy dy dx. So I've just kind of taken out all the extraneous stuff. Okay, I'm going to move this to the other side. This is a plus here, so I'm going to subtract. So dy dx minus 2xy dy dx equals y squared. That's all that's left over there. All right, so I have two terms. Both have dy dx in them, so I'm going to factor out a dy dx. That leaves 1 minus 2xy. Can you see how you might forget that 1? But there are two terms there, so don't forget. And that's equal to y squared. And then the final step will be just to divide. So dy dx, I like making y's evidently, is y squared over 1 minus 2xy. And that is the derivative. Our last example is this one. Consider the curve given by the equation y to the third plus 3x squared y plus 13 equals 0. We want to write an equation for the line tangent to this curve at the point 2, -1. Anytime we want to write an equation for the tangent line, we need to take the derivative. This is implicit form. So we're going to take the derivative. We'll start left to right. I wanted to point out here that this is just power rule, but this is product. So we've got just a little bit of complication there, no biggie. All right, so the first is take the derivative of of y to the third, so 3y squared dy dx plus 3 times the derivative of the first times the derivative of the second plus the second times the derivative of the first, right, plus the derivative of 13, which is 0, equals 0. All right, so I'm going to do one more step, 3y squared dy dx plus 3x squared dy dx. You will probably get much more out of this if you took the derivative, stop the video, take the derivative, and then jump to the end and see how you do it, or watch me do it, compare what you have on your paper. You'll get a lot more out of it than if you're just copying this down. Okay, so the second step said to move the dy dx's to one side and anything without dy dx to the other side. So I'm going to go ahead and combine steps here just a little bit. Okay, equals -6xy. Move that guy over. This is going to be 3y squared plus 3x squared equals negative. All right, so then dy dx will be negative 6xy over 3y squared plus 3x squared. And I could divide all the way through by 3 and end up with negative 2xy over y squared plus x squared. I could do either of those. That would be fine. Okay, so now I have the derivative, but I need the derivative at a point. So I'm going to let x equals 2, and y equals negative 1. And I'm going to have the slope of the tangent line equals negative 2 times negative 1, which is 4, over negative 1 squared, which is just 1, plus 2 squared, which is 4, which is 5. All right, so there's my slope. Last thing to do is to write the equation of the line using point-slope form. My point was 2, negative 1. So y plus 1 equals 4/5 x minus 2. And that is the equation of the line tangent to that curve at that point. So there's a lot to take in. We're going to practice this a lot in class, and I will see you then.